Thanks so much. Thanks for the invitation. I'm really pleased to be here. Thanks, Mingan, for the introduction. Yeah, look, what I'll be just going through today, I'm quite excited because we have some new data that I'm going to be sharing with you today. I'll be focusing almost my entire presentation to feed intake. Although after the recommendation from the previous speaker, yeah, I don't know how much we can do in nutrition, right? But we'll try to review what, in my opinion, it's known to date when it comes to manipulating the diet, especially, as I said, looking at feed intake. And then I'll introduce you to some of the mechanisms that we have been looking. What's behind our work is more than getting the exact level of such and such amino acid. More than that, what we're interested is in understanding the whys. Why is that happening with the principle that if we understand what's going on, then we can apply our knowledge to just any circumstance. So really oops, I think I'm going too fast. Really when it comes to feed intake and feed intake control, I would like to mention the work from Michael Forbes, and definitely when thinking about heat stress, the first thing that comes to mind is uncomfortable, right? You feel quite uncomfortable. And that came to my mind, the theories or the principles of Michael Forbes saying that feed intake basically and hypothetically, it's a game of adjusting the intake of nutrients to the minimum discomfort. That's how animals tend to look at the feed. Do I feel better or I don't feel better? And they adjust that intake as we go on a long-term basis. Now, those nutrients over here, therefore, the optimal minimal discomfort will depend on what type of nutrient we're looking at. So it's a complex balance between energy, protein, amino acids, obviously, and water holding capacity, although this data, I have to say, is from a publication in pigs, but it might be relevant also for other animal species, in my opinion. So feed intake is my theme, and feed intake is what I'm going to be talking about. And as we look at, and I'm not going to go through the physiology in detail of how heat stress and the general stress system works, but it's, I think, relevant to point out that a number of the physiological mechanisms related to stress have a direct impact on feed intake, all right? So let's say when we enter into the activation of the hypothalamus, pituitary and adrenal axis, what you see is an increase in those catecholamines, epinephrine and norepinephrine, which have a tremendous impact on first changing the redistribution of the water pools, blood. So blood just stays away from internal organs, the digestive system, and go to the peripheral tissues. And that has obviously tremendous impact in all these tissues. And I think it's been mentioned before that one of the consequences would be that gut integrity is probably put under pressure, right? So not only, therefore, because the gut function therefore gets disrupted, we will have some leakage, and I'll talk about it a little bit later on, which may interact with the immune system. An immune system that, as the previous speaker said, it's down regulated, it's not so active. It also impacts a number of what we call gut peptides, cholecystokinin, GLP-1, and so on, which have a tremendous impact on feed intake. They are actually the main cornerstones controlling feed intake in birds. And overall, just an overall assessment that let's realize that the hypothalamus, which is the main organ controlling feed intake, is also the main organ in thermoregulation. So thermoregulation, feed intake in the hypothalamus, they are neighbors. That doesn't mean that two neighbors talk to each other. And I see some smiling faces. Yeah, maybe you don't talk to your neighbor, but you know it's easier that you talk to your neighbor than that you talk to somebody else in Australia, right? So overall, what I'm going to be doing is trying to understand some of these mechanisms that are initiated with heat stress and that have an impact on consumption, in chickens. Now, we did, before we started all this project on heat stress, which was not a long time ago, it was about 2-3 years ago, so the results I'm bringing today are quite fairly new. We obviously had a look at the literature, and we looked at what was already known on manipulating the diet that could be related to heat stress. This is a summary of some of the publications that were highlighting potential positive impacts of a number of feed additives, right? This is the case for plant extracts and oils. Somebody has already been mentioning about reducing oxidative stress, maybe gut health. Probiotics and prebiotics, similarly, organic acids and even enzymes, and we do have a speaker that will address enzyme with all the specificity that it takes. But all of these additives have shown at any given time some potential impact on improving heat stress and particularly intake. Now, this is a busy slide, but it's an important one, and I would like to spend some time in explaining what it means. Now, this is a literature review, or almost a meta-analysis if you want, not a statistical meta-analysis, but a meta-analysis. And each one of these dots represent, in fact, peer-reviewed papers that address the topic of heat stress and dietary manipulation. So there's a number of them. But let me say that it was quite disappointing to see that a lot of the papers published on heat stress lack a proper control, which would be, say, a thermoneutral room or environment, right? So you end up, what it looks a lot of dots, but in fact there were probably 5 times more dots on heat stress publications, but I didn't consider them if they didn't have a proper control, because I believe they could be misleading, right? So in any case, what we're seeing here in the center column is feed intake, impact on feed intake of a number of different feed additives, right? And again, these are averages of 5, 6, 10, 12 publications, whatever number we found in each case. Now, what we see is the dark boxes refer to the heat stress treatments, while the white boxes would be the control, thermoneutral. And the line says what happens when the heat stress group gets supplemented with these additives here. So if I push the line towards the right of the dark box, that means that I'm helping to increase feed intake, all right? And getting, hopefully, close to the thermoneutral environment. So as we go across, you will see that there's a couple of feed additives that maybe we should highlight as having an impact on feed intake. And those would be, according to this graph, GLN. GLN stands for papers working with glutamine or glutamic acid supplementation, right? So it would appear that glutamine and glutamic acid, it seems to push the line almost outside the dark box, right? So increasing intake. Similar for arginine and lysine. You see here, increasing the arginine-lysine ratio. It seems that it's also pushing the line outside the dark box, right? And a number of others, like chromium, seems to have also similar effects, or selenium and all that. So that's regarding feed intake, but I would like to drive your attention in something really important. And it's not all about feed intake. Because now if we look across and we see what happens with body weight gain, BWG, you will see that in some cases there's a good relationship. An apparent increase in feed intake, you also see apparent increase in gain, but not in all the cases. So feed intake, when it comes to heat stress, not always feed intake equals improved growth, all right? And we should keep that in mind. And I'll be talking about this later on, because our own data just points at into the same direction. Now, this is the feed conversion ratio column. Now, so I said about the feed additives, but we also looked at, and still in this meta-analysis, we looked at macro and micro nutrients and how they affected heat stress. And I'm just warning that the next slide might look a little bit scary, but I just want to make a point that there's a number of publications addressing caloric density. In general, having a higher caloric density in the diet seems to help. type of fatty acids have been addressed, crude protein, but also some amino acid supplements, as well as vitamins and minerals. Now, this is such a busy slide, and I apologize for the busy slide, but it actually just wants to make the point that I would rank that most of the publications on manipulating nutrients in the diet refer to either energy or amino acid and proteins. And there's therefore a robust evidence that through manipulation of energy, basically increasing dietary energy density and amino acids, we can probably modulate the negative impact on heat stress. Now, it was our objective, and I'm going to be showing some of our data now, that we wanted to reproduce a little bit these paradigms, so playing a little bit with protein and energy, not necessarily to discover anything new, because that was already done, but I wanted to have a model so that I could address mechanisms of how would that happen, what nutrients, when, and why, right? So we had a first approach on playing with low energy versus high energy under heat stress or thermoneutral. And, well, we got a little bit of a surprise. We did have a significant effect on energy for the average daily feed intake, showing that feed intake was increased in low energy, which makes a lot of sense, nothing new there, but we couldn't really find an energy effect on either gain or conversion. Bit disappointed, but I thought, well, no, there's something in feed intake, so we'll keep that in mind. We did a second trial then, testing protein. So what happens with a low protein and a high protein? Again, we were just trying to repeat work that had been done in the past, just trying to get the model right. And, well, what we see was a strong effect of protein for average daily gain and for conversion ratio, so that high protein would improve the heat stress and the growth overall, but not feed intake. No impact on feed intake, but impact on growth and conversion ratio. No? So that was all good. So we thought, right, well, if both trials are pointing at a direction of one low energy for feed intake and the other one high protein for growth, why don't we put them together? So we did. We had a 2x2, 2 levels of energy, 2 levels of protein by 2, heat stress and thermoneutral. And we studied, therefore, whether there was some synergy between having a high protein and a low energy, whether we could reproduce our own data on the low energy. And surely enough, when we look at average daily feed intake, we have a significant effect on protein, so that the high protein here, number 2 and number 4, would just have slightly, slightly lower than but not significantly actually. And the energy intake, the energy effect was significant because the low energy groups 3 and 4 were clearly above the high energy. So the low energy intake again was very significant, and again, it didn't necessarily come up with an improvement of average daily gain, right? But it did say the protein have an impact where high protein had an impact on average daily gain. And it is true that there was no diet to environmental interaction, so that those effects were across environments. So I'm not saying that those effects were only visible with the heat stress treatment, right? Now, now, something that I would like to highlight is the relationship or the association between feed intake and gain. I mentioned before, when we looked at the literature, there's no consistency that, at least in heat stress, feed intake will be driving gain or vice versa. Now, what we've seen here is that in diet 1 and 3, which were the low protein diets, we see a significant relationship between feed intake and average daily gain in both. In the high protein diet, that relationship is lost with, you see, p-values above 0.05. Excuse me. What is that telling us? So that the low protein diet, somehow, the birds are craving for protein. the protein is limiting the development, and that's what I think we're seeing here. And we took that as a sign that obviously amino acids and amino acid related metabolism might be crucial under these conditions. So we took the research to the next step and said, all right, so how is the heat stress, therefore, potentially affecting the sensing of protein and amino acids, in particularly amino acids, right? We do know from humans, mammals, and even birds that when we're under stress, and that includes heat stress, our capacity to sense food and to sense nutrients is diminished, right? In some circumstances and with normal water availability, it may actually increase, but in some circumstances it decreases. Like, for example, one of the reasons is that when we looked at the taste sensory cells in the oral cavity, all these sensory cells co-express these adrenergic receptors which will respond to the noradrenaline and epinephrine, so the catecholamines. So when we're under stress, catecholamines are released from the adrenal gland, and those catecholamines hit the receptors, among others, the receptors in the oral cavity and in the taste buds, so that the taste bud sensitivity changes. How does this sensitivity change? Well, for some type of taste, like salty taste, may slightly decrease. For some taste, like bitterness and even sour taste, it actually increases the sensitivity. So we're more sensitive, we're more alert of what's going on, right? So now the question, and I quite often I talk about taste in avian species, and I often get the question still today that, but birds cannot taste, can they, right? So the answer is the birds can taste at least as well as we can, and I think it's been a bit of a misunderstanding over past years, just thinking that birds were not able to taste, right? Now the evidence nowadays tells us that when we look at the number of taste buds here over body weight, birds are very much in the middle of the graph, so they are as good as you would expect mammalians to be, at least from a, say, anatomical perspective, so from a physiological perspective. Now, in addition, only recent data has been published showing that the number of taste buds in broilers were underestimated. When we looked at the real number that has been published only in the last year or two, in fact, the number of taste buds per size of the oral cavity, it's actually probably much higher than us in humans, right? So I think that's something that we need to keep in mind. So why chickens have been on the spot of not having taste perception? Well, there's several reasons. One is because they don't have taste papilla. Like all of us, mammalian species, we have taste papilla. So all these taste sensing cells are grouped, are clustered in taste buds, and taste buds are in an organelle that it's visible, and that's a taste papilla. In birds, you don't see that because they don't have a taste papilla. So if you're just looking at the tongue or an oral cavity of the bird, you'd say, they don't have taste papilla. They might be probably tasteless, right? But that's not true, because what actually happens is that taste buds are still present in the oral cavity, except that they are not in taste papillas. What is not existing are the papillas, but the taste buds are still there, right? So the capacity is intact, right? So lack of salivation. It is true that birds have small quantities of saliva being produced, not large like in mammals. But what you will see, and that makes a big difference when it comes to the way the taste system works in birds, is that what you'll see is that the taste buds in birds are around the salivary ducts. So the little saliva that's being produced is actually very efficiently used by taste buds because they are in the salivary ducts, right? They are not spread all over. Now, the other thing that it's important to understand is that when we looked at taste in mammals, invariably, always, we look at what? The tongue. But in birds, if you look at the tongue, it's keratinized. There's nothing there. It's just a a physical help to swallow the feed. And actually, the tongue just pushes the feed to the upper palate, and then it's just processed. Now, so where would the taste buds be then? If I push the feed to the upper palate and squeeze it there a little bit, that's the perfect place to actually sense feed, right? So that's where birds have their taste buds, in the upper palate. So you need to look at the right place to actually be able to find the taste sensory system. Now, so there's also known that the number of taste genes in birds is reduced. And that's partially true, partially not true. It's true when it comes to beta taste. We have, humans have 25 beta genes for taste perception, and birds have only 3. But a recent publication from a German group just showed that those 3 taste receptors in birds account for 80% of the bitter compounds in humans. All right? So they are widely tuned, and they are still capable of sensing a lot of different bitter compounds. Now, the low numbers of taste buds is actually probably not true. It used to be that it was 300 for broilers, but now today we know that it's more than 700 using different molecular techniques. So that's what I explained before. That's the salivary duct, and as you see, the different taste buds are actually close to the salivary ducts due to the slow amount of saliva being produced by birds. And this is the genes involved in taste sensing in birds. And as you see, when we looked at sugars, carbohydrates, fatty acids, but also amino acids, all the genes that we know in mammalian species are also present in the chicken. Not all. The T1R2, which is the sweet taste receptor in mammals, is missing in the chicken. However, we do know that chickens sense glucose and sense some sugars through a transporter which we call SGLT1. So I think that chickens still can perceive glucose and simple sugars. But all the rest of the machinery is there. I would like to point your attention to these 2 genes here, T1R1 and T1R3. These are classic, in humans, classic umami taste. So they sense savory, but it's related to proteins. It's related to amino acids, right? When we talk about this, and I highlight this because we have some data about how heat stress affects these couple of receptors. Now, I'm going to skip that slide, but it really says a bit the same that the previous slide. The chicken taste receptor genes are close, relatively conserved compared to mammalian taste system, and those are the homology of different genes from the chicken to human orthologs, right? But I'm not going to stop there. And go ahead with what we know about these genes being expressed in the chicken. And as you know, as you see here, all of the genes that are of interest, including SGLT1, which is the glucose transporter, are highly expressed in the oral cavity of the chicken, right? So they are there, perfectly expressed, similar levels than humans. So there's absolutely no reason why we should believe that chickens are not able to taste to the same extent that we humans do. Now, the most fascinating story about taste is not related to taste. Now, taste is in the oral cavity, perception of nutrients in the oral cavity relates to the gustatory cortex, and that's taste. But the same nutrient senses, the same taste sensory cells that have been described in the oral cavity, they happen to be present in a number of different tissues along the gastrointestinal tract. And they sense nutrients in the gastrointestinal tract, which help then control feed intake by releasing gut peptides, right? So a note on proventriculus, because what we have found over the years is that the expression, the presence of nutrient sensing cells in proventriculus is really high. It's much higher than in the oral cavity. So when we think of taste, we think of oral cavity. Extraorally, we have other organs that express higher levels of these taste sensory cells, and that's related to metabolism and related to control of food intake. Now, in this, I'm going to be presenting some of the very recent data that we have looking at a number of genes of interest, taste receptors for amino acids, T1Rs, calcium sensing receptors, also amino acid sensor, GPRC6A, another amino acid receptor, and GPR92, which relates to peptones, right? We also looked at gastacine, which is a typical biomarker for taste sensory cells. And these are glucose, SGLT1 is for glucose sensing, glucose transporter. And this is a glucocorticoid receptor since we were looking at some stresses, right? And I'm showing only data from the oral tissue and the proventriculus. And we have a number of other tissues that we haven't analyzed yet. So, all right, I'll just be finishing very quick. Now, as I said, there's a very significant, there's a significant effect on tissue. So the expression on the proventriculus outruns the expression on the upper palate. So the proventriculus is an exquisite sensitive organ. And that's the explanation on how those sensory cells, when they are stimulated by amino acids, they release a number of gut peptides that have an implication on the hunger satiety cycle. And one of the main messages today is seeing that particularly these amino acid sensors, T1R1 and T1R3, are upregulated under heat stress conditions, right? And it's sending, therefore, a message of the birds actually craving from some amino acids, and I'll be just very quickly mention. So we do know that these amino acid sensors, amino acid receptors, have affinity for a number, basically all of the amino acids that are relevant for animal nutrition. Now, these are known in mammalian species, but in chickens, T1R1, T1R3 have a very high affinity, extremely high affinity for alanine, a little bit less for serine. And we're seeing that the receptors for alanine and serine in chickens are highly expressed when there is stress, such as heat stress, so something to be considered. And I'm going to, since we're running out of time, what I'll do is just I'll skip all the gut integrity data, but just to mention that there is obviously an opportunity to revisit how gut integrity may have an impact on some of these nutrient profiles. Now, I'll finish up with a summary of what I've presented. And basically, what I've tried to do is, if we look into the literature deeply, we will see that there's some evidences that some feed additives have a potential impact on intake. They can and they do increase intake, especially, as I have mentioned, some of the amino acids and some of the ratios. Now, when we've looked at trying to set up a model, we've seen that low energy is actually increasing quite consistently intake, and the combination of low energy with high protein may actually be quite positive to deal with heat stress. Now, our work on the mechanisms point at some amino acids that we had not considered before, and that might be interesting and important. I said, based on literature, I said about glutamine and glutamic acid, but I'm also saying here that some of the receptors related to alanine and serine might also need to be considered. And with that, I'll just would like to thank Marta, Nadia, Sharam, Sambo, and Beth to work that have been working on these projects, and thanks to them, I've been able to be here presenting this story. So thank you very much.
Thank you, Dr. Roura. This is, I think, a very important new perspective, and it tells us that there is potential, I suppose, by going towards, formulating a balance between the amino acids that could be very, very important under heat stress conditions. Are we getting the questions, Pierre-André?
Do I? Oops.
Whoa.
Oh,
wow.
Not from Santiago. No.
Yes. So if we just go through them one by one as far as we can with the time limit, you did not include enzymes in the group of additives that could help to keep the feed intake. Could you comment on this?
Yes, for two reasons. One, I would say yes, the enzymes, they were in the slide. What is true is I didn't make any specific comment on enzymes because I was just afraid that somebody that knows more than I do on enzymes will be speaking after me. So I said, you know, I'll let Professor Chuck talk about enzymes, and I think that's fair, right?
So, and then there's the other question is then, do you think that we can pre-stimulate feed intake before hatching? I mean, could that help us? But there's another talk about this. Maybe we should skip that one. All right. Because we have a talk on this afternoon, isn't it?
Yeah.
So what else have we got? What about water intake and the capacity of the birds to look for water? Is there, the physiological aspects, could that be related to...
Yeah. There's some sensory scientists that consider water as one taste. And the reason is because taste sensory cells, they actually express a water receptor, which is ubiquitous. It's probably nothing very specific, and that's why the controversy is whether it should be considered a taste or not. But it is clear that we have senses that are specifically addressing water and water needs. So the answer is yes. Birds, chickens do have aquaporins like mammals. So again, when it comes to nutrient sensing, these are very conserved mechanisms in general, and so conserved that we can still see that conservation between such two different animal species, such as birds and mammals.
There's just one more question which I think is fascinating when you look at taste receptors and then thinking about energy replacing like carbohydrates by fats. Does it affect like taste and feed intake? Could that have an influence on feed intake?
Well, yeah, look, in certain stress situations, and I'm going to be referring now to a feather pecking project that one of my PhD students has finished. And what we found with laying hens that are being pecked, their level of cortisol is increased, and they are craving for sugar. So if we include sucrose and glucose in birds being feather pecked, we might be actually helping the weaker birds. Right. So the answer is yes. There is some interesting work about these effects. Yeah, that's correct.
Thank you very much. I think we covered most of the questions, and so that gives us a good idea, I think, about the role of taste receptors in relation to heat stress. Thank you very much, Dr. Roura.
Thank you.